So far we have been looking at Gibbs free energy at standard conditions, 298 Kelvin for solids and liquids, and 1 atm for gases. In this part 3, we will look at how we would calculate the free energy at non-standard conditions and what that tells us about spontaneity, and we will calculate the equilibrium constant using Gibbs free energy. We should see a correlation between a K greater than 1, which means that the reaction is product favored, and a negative delta G, which also means that the reaction is spontaneous in the forward direction. As mentioned in the previous slide, we have been studying Gibbs free energy at standard conditions and when the temperature and pressure are remaining constant. We have determined that when delta G is negative, that means that it is lowering its free energy, and that justifies that the reaction will be spontaneous in the forward direction. But the question is, what if we are not at standard conditions? We will use the equation at the bottom to determine if the reaction will be more spontaneous or less spontaneous at non-standard conditions. So let's take a deeper dive into this equation. You'll notice that the delta G on the left of the equal sign does not have a degree sign. That is the free energy change of the gas at a specified pressure, which will be at non-standard conditions. That means that the pressure will be different than 1 atm. And then on the right-hand side, we've got delta G standard, which is the free energy change of the gas when we are at standard conditions, which is at 1 atm. And we will be adding that to a product where we will be multiplying R, which notice is 8.3145 joules per Kelvin mole, times temperature, which must be in the Kelvin scale, times the natural log of Q. Remember, Q is the reaction quotient, and that is a ratio of the partial pressures of the products over the reactants. What's most important here is what's in yellow. After we determine the delta G at non-standard conditions, if that value is higher in magnitude, meaning more negative, meaning it will release more energy than delta G standard, then it will be more spontaneous at those non-standard pressures. Most of the time, we can do these problems without actually doing any work. If we are given enough information, we can use the Le Chatelier's principle, and we can look at the reactant concentration versus the product concentration. And so if the reactant concentration increases, which is on the bottom of the reaction quotient, that will cause Q to get smaller. And if Q gets smaller, the reaction will proceed to the right towards products, and the reaction will thus be more spontaneous at those non-standard conditions. So let's jump into example 11. Would the reaction be spontaneous at 25 degrees Celsius with the partial pressure of hydrogen being 3.0 atmospheres and the partial pressure of carbon monoxide being 5.0 atmospheres? So the first thing that I'm going to do is I'm going to realize that I'm not at standard conditions, and I'm going to need to use this equation in blue. So in order to use that equation, the first thing I'm going to do is I'm going to calculate Q. Remember, Q is a ratio of products over reactants. We never use solids or liquids, so that's why it is 1 over the partial pressure of carbon monoxide times the partial pressure of hydrogen squared. I'm going to plug in my partial pressures, and I get a Q of 0.022 atmospheres. So I'm going to pop that into this part of the equation. Of course, the temperature is going to be at 298 Kelvin, and I'm going to use an R value of 8.314. I'm actually going to change that to 0.008314 due to the fact that the delta G is going to be in kilojoules and the R value is in joules, so we do need to make that necessary adjustment. I'm then going to calculate the delta G at standard conditions using the sum of the free energy of formation of the products minus the free energy of formation of the reactants. That's going to give me negative 29 kilojoules, and I will add that into my equation. That's going to give me a delta G of negative 38 kilojoules at non-standard conditions. Remember that the higher in magnitude of delta G, the more negative the delta G, the more spontaneous the reaction will be at non-standard conditions. Because remember, that's the amount of energy that is being used up as it approaches zero. We can also look at this qualitatively with Le Chatelier, and you can see, based on the partial pressures of hydrogen and carbon monoxide, which are reactants, will increase. Thus Q will get smaller, and the reaction will shift to the right to try to reach equilibrium. Thus, the reaction would be more spontaneous at non-standard conditions, or we could say is more product favored at non-standard conditions. In example 12, we're going to be doing the same type process. So you'll notice the first thing that I did was calculate Q, because I noticed that I was at non-standard conditions. I then plugged in my information to this equation, making sure that I change the R value to kilojoules, since the delta G standard was in kilojoules, and that's going to give me a delta G at non-standard conditions of negative 50.7 kilojoules. Remember that if the absolute value of delta G is less than delta G standard, that means that the reaction would be less spontaneous at non-standard conditions. We can also look at this in regards to Le Chatelier. We know that the product concentration is increasing, the reactant concentrations are decreasing. That means that Q will be greater than K, so the reaction will shift to the left in order to meet K, which means that the reaction is reactant favored, and thus it will be less spontaneous in the forward direction. Example 13 is just like the last two problems. We are at non-standard conditions, so the first thing we're going to do is we're going to calculate Q. Notice that the products are decreasing in concentration and the reactants are increasing in concentration, giving us a Q that is going to be less than K. We would assume the reaction will proceed to the right in order for Q to match up to K. If we actually do the math, we will see that the answer tells us the same thing. As we plug in all the information, we get a delta G at non-standard conditions of negative 129 kilojoules. If the absolute value of delta G is greater than that of delta G standard, the reaction will be more spontaneous at those non-standard conditions. Remember, we're looking for energy to be used up, free energy to be used up, and the greater the magnitude, the more energy will be used up. The last thing we need to look at is the relationship between free energy and equilibrium. So we've been working with delta G, free energy, and we know that that gives us information about the spontaneity of a reaction. Will the reaction be spontaneous in the forward direction? But when will the reaction stop? The equilibrium constant will give us some of that information. It is important to know that the reaction will proceed to the lowest possible free energy state, which could be equilibrium. At equilibrium, delta G will be 0. If delta G is 0, then we are assuming that Q equals K. Using the bottom equation, we will be able to go back and forth between calculating K, the equilibrium constant, and delta G, free energy, at standard conditions. Notice the relationship. When delta G is equal to 0, the equilibrium constant will be exactly 1, and we are at an equilibrium state. If the delta G is less than 0, which means that it is negative in sign, then that would assume that the reaction is going to proceed in the forward direction spontaneously, and thus K would be greater than 1 and product favored. And if delta G is greater than 0, which means it would be positive in sign, we would assume that it is not spontaneous in the forward direction, thus it would be reactant favored, and the K value would be less than 1. Example 14 is asking us to calculate the equilibrium constant for the formation of ammonia. And in order to do this, we must know the free energy change. I am actually going to give that to you. It is in the blue box. We can now substitute that in to our equation. Remember that the R value has to be in kilojoules, so we're going to switch it to 0.008314. Temperature has to be in Kelvin, and we are going to be solving for the natural log of K. After plugging it into the calculator, we will get natural log of K is equal to 13.44. If we take the inverse log of 13.44, our K will be equal to 6.59 times 10 to the 5th. That means that the reaction is product favored, and that correlates to a negative delta G. Both tell us that the reaction will proceed in the forward direction. This last slide has information that you will most likely not need on the AP exam, so we are going to skip this last slide. And that concludes our Unit 14 spontaneity presentation. Make sure you are working through all of the problem sets and that you are reading through the textbook if you need some more information on this. And hopefully when we get back, we can do a quick review of this unit and move on to our last unit, which is electrochemistry.